Hi, I'm Paquita. I'm a professor at University of Miami involved with CSET. I'm here in the Seattle Operations Center, and we're very excited about this field experiment. So we're looking at this stratus to cumulus transition regime, which, as you can see in this visible satellite imagery, it's a very complex regime, and the cloud fraction changes dramatically between Hawaii and California, the domain that we're studying in. And for this experiment, we have the use of a new plane, this G5 plane, which has the unprecedented capability of reaching Hawaii all the way from California, so that we can really interrogate these subtle changes that happen in the clouds along the way that are responsible for the cloud changes. So, right. So here you can appreciate, the larger synoptic scale influences on the cloud evolution. And what the plane will allow us to do is to sample the same air mass at a couple of different times. So what's called Lagrangian sampling, rather than in most experiments you mostly sample the air that's moving above you. But here we can actually try to assess how the same air mass is evolving in its state as it's moving. So I'd like to show off some of the tools. Oh, and something I wanted to show in here is you can appreciate the synoptic influences on the clouds. There's also aerosol influences on the clouds, and one measure of that is a cloud droplet number concentration from satellite. You just see these large variations in the number of droplets in the clouds, which we think may have something to do with all the smoke that's been outflowing from the wildfires in Canada. So we also have access to some new tools that make this very productive experiment for us. One is that we can chat directly with the people on the aircraft. So here I am in Seattle. This plane has taken off from Hawaii a couple of hours ago, and we can communicate, real time and know what's going on the plane, and just feel like we're part of the action, even though we're down here on land. And we also have data that is being that we're able to see real time. So here, this red line here is the altitude trace, and so the airplane is descending right now as it's getting ready to do its first profiling of the cloud deck. The blue line here is the wind speed that's associated with it. Here we can see the temperature and the dew point temperature, so this gives us a moisture, gives us a sense of the relative humidity that the cloud is developing or not developing in. And another really important measurement for us are the aerosol concentrations. So there's three aerosol numbers on here. One is the total concentration count. That's this red one. It looks like it might have had a spurious spike. Maybe it went through a smoke plume or something, or somebody else's aircraft exhaust. And the blue and the green are aerosols that have been cut off at certain size thresholds. So these shallow clouds are complex because there's much more mesoscale organization to them than we had originally appreciated. But they're still weakly forced enough that aerosols are also very important in their makeup, how their susceptibility to precipitation. So we need both measurements, and we need to be able to understand the wide range of scales that are involved, from these really nanoscale aerosol sizes to the large synoptic scales. So that's what we'll be what we'll be trying to do with this experiment, and our tools to do so keep increasing in what we can do every year. And I guess the last thing I'd like to wrap up with is that we have these new tools with which we can look at the data sets real time, and these are aiding our ability to plan future missions, but they're also very useful for educational purposes. So we can recreate these same plots after the field experiment and use them in our classes, which is really fun too.